this and that. And then I mumble something, I point somewhere and I run away because I know nothing about that stuff. But luckily, Alessandro is a master of these arts, luckily for us. And so he will telling a bit about how we are actually using, how actually Docker helped us improve a lot in terms of reliability, scalability, and a lot of things. And we are actually using Docker also for things that go beyond the pure scalability concept, as we'll see. So please, Alessandro, take the floor. Thank you.
Thank you, Mr. President, for the very nice introduction. Hi, everybody. Thank you for staying until the last talk of the day. My name, as Lorenzo said, is Alessandro, and I'm one of the co-founder of Miteco. In this talk, Janus and Docker, friends or foe, I'll try to show you how we used to deploy Janus as a microservice within Docker, the issues that we encountered, and how we managed to solve them. Oops. A quick overview of this talk. First of all, I'm going to introduce Docker as the main solution for realizing microservices today. Then I'm going to present Janus as a microservice. So I'm going to talk to you about how we deploy Janus mainly within Docker containers. And I will give you some information about how Docker networking works, because as we will see, most of the issues that we encountered can be somehow reconducted to the Docker network behavior, to network in general. Finally, at the end of this presentation, I'll show you two examples of complex Docker-based architectures that we realized that we implemented and maintain, that are the IETF remote participation system and the cluster for the production of video recordings out of Janus. Applications have transformed. We have moved from the big monoliths we had in the early 2000s that were running on big powerful servers and were kind of difficult to maintain and update, to let's say a puzzle of loosely coupled services that run on many small servers or also small devices like Raspberry Pis, and that interact among each other in various ways. Such loosely coupled services are called microservices, and here we have the definition of microservice taken for Wikipedia. I'm not going to read it. It is quite straightforward today when you think at microservices to think at Docker and software containers in general. Docker, in fact, is the de facto standard for realizing containers nowadays. It is an open source platform for developing, shipping, and running applications containerized. And the particular thing about the containers virtualization technology is that with containers, the guests all run within the context of the same kernel. And in other words, they share the kernel of the host machine, the Linux kernel of the host machine. So with containers, you basically don't have a guest operating system, a virtualized RAM or CPU or whatever, but just all containers share somehow the same set of resources. Of course, containers are still isolated from each other, but can share resources like networks, file system volumes, and other stuff. Of course, you all know what Janus is. I just stole this slide from one of Lorenzo's decks because I wanted to put the circled R, the registered trademark symbol, there next to Janus, because, yeah, we registered the Janus trademark both in Europe and in the US, and that's cool to say, basically. So let's tell you something about our deploying experience with Janus. Janus is a small footprint and relatively lightweight piece of software that can be easily deployed pretty much everywhere. You can install it on bare metal servers, on virtual machines, Docker containers, cloud instances that are virtual machines themselves, or on a mix of the above. A mix of the above, this kind of a hybrid approach is actually quite common nowadays. In fact, it is not that that unlikely that you, while you are in your production phase, in your development phase, so you are developing your application, your WebRTC based server, you just use containers to run your application and test it and all the things. When instead you need to go in production, you can get your hypervisor-based virtual machine. You can install Docker in it and still run the very same containers that you have tested in a controlled environment in your lab setup on your production machine. And this is actually what we do for the IETF remote participation system that I'll show you towards the end of this presentation. We have been deploying Janus within Docker containers for a long time now, both for ourselves and for our clients. And what I can say is that most of the issues we encountered, most of the failures we experienced, can be somehow reconducted to the network, to the network behavior. So you can always somehow blame the network. And our friend Con here, that is the guy wearing the shirt in the picture, Con is one of the members of the IETF NOC team, will forgive me for saying so, because in this case, this is actually true. You can actually blame the network, as I will show you. Different networking modes are available for containers. And for example, a container can use directly the network of the host machine, or can be behind a NAT, or have a dedicated IP address dedicated to it. Choosing the most appropriate network mode is one of the key challenges that you have to face, and that can have a huge impact on the results you're going to achieve. And I'll give you a spoiler: assigning IP addresses to container is the best solution, the best choice you could make. So let's see briefly how Docker networking works. The container networking model, the CNM, specifies the networking architecture for containers, and it specifies sandboxes by means for realizing networks isolation, endpoints by means of which a specific container can be plumbed into a specific network, and networks themselves. libnetwork is the Docker native implementation of the CNM, and it leverages the Linux kernel implementation of the network stack. So to some extent, the Docker networking is Linux networking. Different network behaviors are realized in Docker through the so-called network drivers, and Docker provides out of the box 4 different built-in network drivers that are the host driver, the bridge driver, the overlay driver, and the MacVLAN driver. I will try to briefly introduce most of them in the next slides, because 3 of them are actually suitable for running a container, a Janus container. I just will skip the overlay driver because it is out of scope here, because it is basically for inter-host communication. With the host driver, for instance, containers use directly the network stack of the host machine. There is no namespace isolation, and all host interfaces can be directly seen and used by the guest containers. It's definitely the easiest networking mode available in Docker. It is suitable for running, for instance, a Janus container, as long as you don't need to run more than 1 Janus container per machine, per host machine. And I'm saying so because you need to take care of avoiding possible ports conflicts. For instance, as you know, the Janus HTTP transport listens by default on TCP port 8088. And if you have a Janus container running on a given Docker host, which is configured with the host network, and then you want to run a second Docker container, or a second Janus Docker container also running with the host network, you should take care of properly configuring it so that it listens on a different port. So you should properly manage this specific configuration. And the same applies also for port ranges that you may want to define for media traffic, for SRTP traffic, for instance. So using the host network in this case limits the number of containers that can be run on the same host machine, and also handling things like auto-scaling. So let's imagine that you want a new Janus container to automatically be spun up when your load goes beyond a certain threshold. This is also kind of difficult with the host networking because of the ports conflicts that you have to handle. So the specific particular configuration that you have to make on a case by case. The bridge network instead implements NAT functionality, and it's the default network mode of Docker. This means that if you don't specify any network driver when you run a container, your container ends up being NATted. Container on the same bridge network can communicate over local area network, over LAN. Containers instead on different bridge networks need routing in order to reach each other. Also here, ports mapping is needed for reachability from the outside. The bridge network gives you the possibility to publish ports. That means establishing a mapping between the host machine and the guest container in order to realize the reachability from the outside. And also in this case, ports conflicts need to be properly taken into account, because if you map the same range of ports, for instance, for two different containers running on the same host, you will end up having the second container that you run not being started because of a port conflict. At the first glance, the Docker's NAT behavior seems to be address independent. More precisely, it seems the Docker NAT seems to behave like a port-restricted cone NAT. This means that an incoming packet that is seen by the Docker NAT is allowed to go through only if previously it has detected an outgoing packet that is addressed to the very same transport address as the incoming packet. About this, a quick parenthesis. If you're interested in checking out which type of NAT your Janus instance is behind, you can leverage the newly enhanced test stun feature that Janus provides via its admin API. This is interesting because it basically allows you to send arbitrary stun requests and read responses by also specifying the source port of the datagram that is going to be sent. And you can exploit this to learn the type of NAT that you're behind, basically. In a development environment, like for instance the one that is depicted here in the slide, using the bridge driver is quite a common choice. When you are in the development phase, it is quite common to leverage the bridge network to host your container, for the container you're hosting. Actually, I've been struggling a lot to find a valid, a credible reason to run containers in production using the bridge network, and I failed. I failed until Lubo came with this very interesting presentation today, which actually showed us that they are deploying Janus in production by using the bridge network, and this is very interesting because now I can say, why should you use the bridge network in production? I can answer, because Peter does. And that's a very good answer. I was saying that in a local environment, it is quite common to use the bridge network for your containers. And in this environment, in this controlled environment, iSetup is expected to succeed thanks to peer-reflexive addresses. Actually, what we found out was something different, because we experienced random ICE failures. We started diagnosing such failures, and it took quite a lot of time because it was not that easy. And by further digging, we found out that the streaming plugin of Janus was mostly affected by such failures. The EchoTest plugin instead seemed to be immune. The video room plugin finally was only affected for the subscribers and not for the publishers. This gave us some good hints. And finally, eventually we found out that the failure depended on who sends the JSAP offer and who answers. When the browser offered and Janus answered, everything was okay. I succeeded and we were happy. When Janus offered and the browser answered, ICE failed. We tracked down this behavior to libnetfilter. That is a library that is used by libnetwork. That is the library that is used in turn to implement the container networking model. And long story short, what we found out is that the Docker NAT is not address independent. At least it is not always address independent. It is most of the time. But there are edge cases where it acts as a symmetric NAT. And you know that a symmetric NAT is an ugly beast when dealing with any session-oriented protocol. I'll try to better explain this with the help of this sequence diagram that I'm afraid you won't be able to read from the back of the room. Sorry about that. This is an example of an ICE failure. So let's imagine a streaming plugin session. We have Janus that creates its offer, gathers its candidates, and sends them in the SDP that he sends towards the client. This is because Janus by default is configured to do half trickles, so it doesn't send trickles candidate itself, but nothing changes if Janus is configured to do full trickles, so to also send trickles candidates. The browser gets the JSAP offers, gathers its candidates, and then sends the JSAP answers and trickles its own candidates. Right after that, the browser is capable of starting the connectivity check phase because it's on all ICE credentials and has already formed all the ICE candidate pairs. So it starts sending a stun request from, let's imagine, its source port for 40,000 and addressed to destination port 20,000. That is the port that has been announced, advertised by Janus into its candidates. This stun request gets to the Docker NAT and it is blocked as expected. The weird things, the interesting things, the thing is that the subsequent stun request that is sent by Janus from its source port 20,000 is mapped on a different transport address by the Docker NAT. You see there that you can see there that the source port of the packet that is forwarded by the Docker's NAT has been mapped on ports 1024. And this weird behavior is caused by this packet. This incoming packet that has been blocked has caused the libnetfilter to somehow, let's say, reserve the port number 20,000 for a possible future connections addressed to the IP address of the Docker host on the very same port. This is done with a very small timeout, I think 10 or 15 seconds, I don't remember precisely, but anyway, this caused the symmetric NAT behavior that I anticipated you in the previous slide. One thing you may notice in this slide is that I put a further NAT in front of the browser, in front of the client here in the slide, and I'll get back to that in a few seconds. This is instead an example of ICE success. Here we have the browser that sends the offer and Janus sends the answer. So Janus basically is the first one to complete once again the ICE candidate pairs and can start its connectivity check phase. In this case, the stun request that is sent by Janus is mapped by the Docker NAT by preserving the source port address. So here we have actually an address-independent behavior of the Docker NAT. This request gets to the client's NAT and is blocked as expected. The different thing is that when the browser itself sends its stern request, this stern request here is allowed to go through the Docker's NAT. And this happens because of this message here that has opened a hole in the NAT, and given that the NAT is behaving not like a symmetric NAT but like an address independent one, the communication can successfully be established. So what are the takeaways? Docker networking can be tricky when dealing with ICE. Both hosting networking and ports mapping are not ideal when you want to do things like auto-scaling, and also can limit the number of containers that you can run on the same host machine. NATted networks should be fine in a controlled environment, but things get weird when the browsers are also behind NATs. And this is actually not unlikely, and that's why I put that further browser in the previous slides here in front of the browser, because we discovered that, for example, Firefox multiprocess has a built-in UDP packet filter that doesn't allow a stun check to get to the browser, to get through an incoming stun check, unless an outgoing stun check addressed to the very same port address has been previously detected. And just to clarify, the Firefox multiprocess that I'm talking about has been around for almost 2 years now, so this is not something very recent. Things get even worse with the new obfuscation of host candidates that is going to be pushed, the new obfuscation of host candidates through MDNS that is being pushed, that is has already landed in both Chrome and Safari, and is about to land in Firefox 2. So dedicated IP addresses to containers for the win. The best choice, as I anticipated you, as I spoiled you, is to assign dedicated IP addresses to your containers, no matter what environment are you actually in, what network environment are you actually in. This can be done in Docker in 2 different ways, either by using the MacVLAN network driver or using a tool that is called Pipework. With MacVLAN, you can expose host network interfaces directly to containers. And MacVLAN is a Docker native network driver that is available out of the box and allows a single host physical interface to have multiple MAC and IP addresses that you can allocate, you can dedicate to containers. In this case, so you don't have any need to do port publishing, port mapping. And in this picture here, you can see that we have in the same hypothetical local area network, that is the 10.0.0.0 network, you have a Docker host that is hosting 2 different containers and also a virtual server and a physical servers, and all of them have an IP address on the 10.0.0.0 network, so they are able to communicate over LAN no matter what. Pipework instead is a tool that I've been using for a long time, and I still use actually because I really like it and I find it very effective. In fact, with Pipework, you can basically achieve the same results as the MacVLAN driver. And actually, we started using Pipework because at the time, the MacVLAN driver was not even available in Docker. In fact, you can create a new network interface inside the container and set networking parameters like IP addresses, netmask, default gateways, and the like. And this new interface becomes the default one for the container, no matter the type of network that you may have selected at the container startup. It works just fine also with IPv6, with the only caveat that if you want to use both v6 and v4, your v6 interface has to be created first. Otherwise, it doesn't work. As promised in the introduction, here I show an example of a complex Docker-based architecture that includes a number of microservices, including Janus, of course. This is the IETF remote participation system. And just to give you some context, at IETF meetings, the NOC team deploys bare metal servers at the meeting venue. And on these bare metal servers, they spin up virtual machines with a Ganeti KVM hypervisor. And 4 of these virtual machines are dedicated to the remote participation services. So on these VMs, we run a bunch of containers. Namely, we have 5 different containers. We have Janus, of course. We have Asterisk, Tomcat, Redis Plus, Node.js, and Nginx. All these containers are glued together by sharing the same network stack so that they can basically communicate over the loopback interface and have public IPv4 and IPv6 addresses allocated to them via pipework. These 5 instances together, these 5 microservices together, constitute one single instance of the remote participation platform that we provide to the IETF. And actually we deploy 8 different instances of this remote participation platform, 1 per each physical room that is available at IETF meetings. These 8 instances are split on 2 different VMs, and while a third VM is left idle for failover purposes. This means that if anything goes wrong and the node, let's say, goes down for whatever reason, we have the tools to migrate all containers that were running on that specific node to a different Docker host with a minimal interruption in the service, like a few seconds of interruption in the service. The 4th virtual machine finally hosts some utility services like a turn server, a stats collector, an authentication server, etc. Coming to the very last part of this talk, I want to introduce a solution we realized for producing audio-video recordings for Janus, which we called Melter. As you may know, Janus records individual contributions into MJR files, as we also saw from Marco's presentation. These MJR files are basically a dump of all RTP packets that have been received by Janus, plus some metadata information that is contained into a header. MJR files can be converted into the corresponding playable files by means of the Janus pprec utility that is shipped with Janus as long as you compile it with the enable post-processing flag. Such individual contributions can then be merged together into a single audio-video file, for example, via well-known libraries like FFmpeg, like Marcos did in the previous talk. Timing information here are important and need to be taken into proper account because you need to sync audio with video. And also there are some other information useful that are contained that can be obtained by parsing the output of the pprec utility, like for instance the time of the first keyframe that is received and written into the MJR file. Just because any video frame that you receive prior to the first keyframe is just garbage, you cannot decode it and you can trash it. Melter is a solution we developed for converting all MJR files belonging to the same session into a single video according to any given layout. We implemented it by leveraging the MLT media framework. All post-processing and encoding jobs happen within containers on a cluster of machines that is orchestrated via Docker Swarm. We actually started with CoreOS and then migrated like 1 year ago, I think, to native Docker Swarm mode. Okay, I'll skip this slide because I'm kind of running long. This was just to give you some information about Docker Swarm, what Docker Swarm is, that I hope you are already familiar with. When we designed Melter, we wanted to leverage a number of bare metal servers we had available at our premises. Namely, we had 2 big powerful servers to rack servers, and 5 less powerful but still very good workstation that we wanted to use for the purpose. The picture here shows the Matter cluster as it is today, with the 7 different machines that I just mentioned, plus the network storage and NAS to write and read data from. We wanted to properly partition, let's say, these machines so that they can host as many containers as possible according to each node's hardware characteristics. So we wanted the possibility to somehow set the maximum number of containers that can simultaneously run on each Docker node, on each Docker Swarm node, according to the node's specs. This feature was missing in the Docker Swarm API, and as far as I know, is still missing today. The solution we came up with is to exploit Docker networking once again in a, let's say, a hacky way. What we did is to create on each Swarm node a network configuration, and this network configuration will have a limited number of IP addresses available. This is done via subnetting. For example, in this code snippet here, the first code snippet, we are defining a /29 subnet. This means that theoretically you have up to 8 available IP addresses. Actually, we limited such number of available IP addresses with by using the --aux address option that basically excludes one IP address from the available ones. So in this example here, we end up having 6 available IP addresses because we excluded the 0.1 and 0.2 addresses. Of course, this configuration has to be replicated on all Swarm nodes, and you must make sure that you choose non-overlapping ranges of IP addresses for the various nodes. Only on the Docker Swarm Manager, instead, you need to create a Swarm scoped network from the defined config, for example, with the code snippet there. I'm super long. Once the configuration of the cluster has been completed on all nodes, the manager can schedule then containers, conversion jobs on the Swarm nodes by using a Swarm stack descriptor like the one that is depicted here that we developed for IETF recordings. Each container is plumbed into the meltnet network that we defined, and if a node runs out of IP addresses, new containers will not be allocated there until one IP address becomes available again. And this is how we achieved our goal to stop the allocation of new containers and to set a maximum number of containers that can be run on a single host until one conversion job completes and then a new one can be started. And you can set different maximum values according to the node's hardware characteristics. Containers also leverage the NFS volume driver, as I said, to read and write to a shared storage. And this is a sample output of a conversion job, and then I'm done, I promise. I was just interested in pointing out that this was an IETF recording, the recording of an IETF session. In this example here, this recording envisaged the different Janus plugin. It was made out of MJRs that came from different Janus plugins. In fact, at the IETF, we managed the audio via the SIP plugin. The 2 videos, the slides feed, and the videos from the local speaker, that is one in the top right corner in this picture, are handled via the streaming plugin. And finally, the remote speaker there is just a video room feed. And I think that's it. Yeah, thank you for your patience, and I'm happy to take questions.
Thanks, Alessandro. I see Ole with his hand raised already.
I have 2 comments. First, I want to thank you for mentioning IPv6 with this fabulous sticker.
That was my goal.
Yes. Secondly, I spent many, many years and too many napkins and destroyed a lot of whiteboards discussing how to communicate between two devices but behind two different NATs. And that's just pure hell. And that's exactly why we invented ICE and turn. And you never mentioned turn. Why didn't you mention that? You tried to
You're absolutely right.
break the network.
Yeah, I should have mentioned that. Should have mentioned that in our experiments we deliberately didn't configure a turn server because we wanted to. Absolutely, but when you are in a testing, a development, and in a testing phase, you want to test things that where they are supposed to go right. So turn should be left as the last resort. So you don't want all your sessions to end up on a turn server. So if you think that your connection should succeed without a turn server, and actually you end up being on a turn server, you got a problem because you made something wrong in your design phase. And absolutely, I do agree.
I see Anand in the back there.
I have a fundamental question about Docker and microservice. I realize if you have different microservices, you spawn different Dockers, but the same Janus microservice, why spawn multiple copies of that on the same host? You just increase the number of, like if you're running out of CPU, just bump it up to the maximum, right? Like what's the point in allocating multiple Janus instances on the same host as opposed to just maximizing that microservice to run as much as it can and gas out of CPU or bandwidth or whatever?
Yeah, that's a good question. Actually, there may be different answers. So the first one that comes to my mind is that a single Janus instance may have limits that are not determined by Janus itself, by some of the libraries it is based upon. And I can make you an example. Janus heavily depends on libnice, that is the library that provides all the ICE stuff. And up until a few months ago, libnice had a performance bottleneck that didn't allow you to have more than a certain number of peer connections on the same Janus server. And so you were actually blocked not by reaching the maximum amount possible of the host machine, but you were hitting a bottleneck that was determined by libnice. And by replicating Janus, even on the same Docker host, by duplicating it, you may actually double the number of peer connections that you could handle.
Some more questions for Alessandro?
Hi, I was wondering if there is a solution for libNetFilter that you mentioned for the symmetrical NAT, or at least.
Can you please come again?
I was wondering if there is a libNetFilter solution for the symmetrical NAT behaving differently all the time. So, is there a bug report or anything?
No, I don't. No. There is no solution because actually there is no real issue because libNetFilter has been conceived to handle networking in Linux and is also used in many Linux routers. But the difference with the Docker host is that it is a network host itself. So it is supposed to handle packets addressed to itself. And so it does have to, let's say, somehow preserve this possibility. So the small timeout that I mentioned that basically forces the symmetric NAT behavior in the experiments we made was actually determined by this thing, that the Docker host has to handle packets addressed to itself. It is a network host. It doesn't only host containers, but it is also capable of sending and receiving packets coming, for example, from different applications.
Hi. So when you design this recording solution and you record each stream individually and then have to put them together with the metadata, do you have the use case where you do different mixes, or is it mostly like the one layout that you just do it all the time?
You can specify the layout by means of a JSON file that you pass to the post-process to the melter thing. So basically, if you want to achieve different layouts, all you have to do is to pass different JSON files and do the encoding process twice, of course.
Yeah, I realized that. My question was more around practically. Have you guys, while doing these IETF recordings, for example, have you been using multiple layouts, or is it mostly what the participant would see while joining via browser would see? Are you replicating that or doing some other different thing?
Yeah, pretty much we are replicating that. We are giving priority to the slides because usually is the most important content within an IETF working group session. And then we have this mosaic of video feeds coming from the local room and from possible remote participants.
So then the real question.
You were tricking me.
Yesterday we were, a few of us were gathering, and there seems to be this way of doing recordings that we're all doing, but we're kind of ashamed to talk about it because it feels like duct tape on steroids. It's basically spawning a VM running a browser and record the output using FFmpeg, and this is so ugly, but it works so good in practice. What are your thoughts on it, if you have any?
What are my thoughts? I don't really like the approach. I must be honest. I think it is also kind of let's say overkilling. It's heavy. Spawning a browser that records everything for.
But you need a cluster. And
yeah, but I need a cluster that does post-processing. So I have all the contributions, and I can then pass all the data to this cluster that does post-processing. If I have to fix something, if I have to eliminate, let's say, a broken video because somebody just had his webcam covered with a sticker because he didn't want to show himself, but he did accept the permission to share his webcam, and I don't want this contribution to be in the actual video because it would be ugly. I can do that by just removing the individual contribution and post-process everything. This is one of the first things that comes to my mind.
All right, thanks.
Sure.
Just as a side note, we also have a different way of recording media that we don't advertise as much, mostly because we don't use it as often, but it's basically RTP forwarding media from a room to a separate video mixer that uses a similar kind of JSON-based layout that you can change on the fly using commands, which does pretty much the same thing as the melter does, but in real time. So that basically also is theoretically a bit more heavy than this approach, less scalable, but it still should be a bit better than that one.
I have a very IETF specific question, and this may touch some of your corporate secrets, but seeing Eric up there, how is the process with your AKR parser? Because I've been a JabberScribe many times in a room with him, and I wasn't able to follow.
Nobody can parse Seeker.
Even if you throw a lot of CPU on him? No? Okay.
No, it's impossible.
Thank you for the answer.
Thank you.
Oh, okay.
And I put the sticker, by the way, only.
Any more questions for Alessandro?
Is it for real that you have seen people in the IETF meetings covering their webcam with us?
Absolutely.
Really? Okay.
Do you have doubts?
People in meetings about WebRTC, I mean.
About meetings about WebRTC, I don't know. Probably yes, I cannot say, but IETF is not all about WebRTC.
Yeah.
There is a lot of other stuff, and you would be surprised. Don't let me tell you more.
Nice, thank you.
Then thanks, Alessandro. Let's give him a big round of applause.